Hi everyone, it's Mr. Forster, and this week's lesson is a fun lesson. It's about powers of 10 and scientific notation. If you remember last week's lesson about exponent rules, this kind of builds on that, but powers of 10 are special types of powers, and scientific notation use powers of 10, so they kind of go together. So here we go. So let's talk about a power of 10. It's a concept in math that uses exponents to describe place value. So if we know 10 to the first is 10, 10 to the second is 10 times 10, that's 100. So we see here the tenths place value, the hundredths place value. 10 to the third is 1,000, that's the thousands place value, and so on. 10 to the fourth is the 10,000. You notice 10 to the fourth has 4 zeros, 10 to the fifth has 5 zeros, 10 to the sixth has 6 zeros. And so that is just a kind of an introduction to powers of 10. And they are place values. And so now that you see the pattern with the powers of 10, the positive powers of 10, we know anything to the 0 power is 1. And then 10 to the negative 1, well, that's 1 over 10 to the first. We learned about negative exponents last week. That means it's on the other side of the fraction bar. That's 1/10 or 0.1. And 1 over 10 to the negative 2 is 1 over 10 squared. 1 over 100, that's 0.01. And then 0.001, 0.0001, and so on. So that's tenths, hundredths should be a 0 there. Thousands, 10,000s, 100,000s. So again, the small place values, fractional place values. 10 to the third, and we talk about order of magnitude. So 10 to the third is an order of magnitude bigger than 10 squared. So we use this vocabulary, order of magnitude. Well, 10 to the third is 1,000, and 10 to the second is 100. So 1 order of magnitude is times 10. So if you're off by an order of magnitude, you're off by times 10, which is a problem if you're doing math. So an order of magnitude can be a big difference. It's times 10. And so a real-life example of powers of 10 is the Richter scale for measuring the strength of earthquakes. And so a 6.0 earthquake can be thought of as 10 to the 6th power, while an earthquake that is 4.0 can be thought of as 10 to the 4th. And so the question is, well, 10 to the 6th, a 6.0 and a 4.0, those are about the same, right? Well, the answer is they're not. So how many times bigger is a 6.0 than a 4.0? That's a division problem. How many times bigger? So we divide 10 to the 6th divided by 10 to the 4th. And if you remember, you subtract the powers. It's 10 to the 2 times bigger, or 100 times bigger. So a 6.0 earthquake is 100 times bigger than a 4.0 earthquake. Just some information for you that when we use powers of 10 or magnitude. Scientific notation. Scientific notation is an offshoot of powers of 10. So scientific notation is a more efficient method of writing very large or very small numbers using powers of 10. Remember that powers of 10 represent place values. So here's an example of a large number. And scientific notation uses this power of 10 as a factor, and then we use 1 digit and a decimal and 2 decimal places. This is the classic way to write scientific notation. You could use just 1 digit and a power of 10, but so anyway, here's the number 123. Notice I use 1, 2, 3, 4, 5, 6, 7, 8, 9, but it's 123,456,789. And in scientific notation, we know that this 100 million, that's 10 to the 8th. So that's 10 to the 0, 1, 2, 3, 4, 5, 6, 7, 8. So it's 1.23. That's where we want to put the decimal. And of course, if this was a 5 or more, we would make it 1.24, but that's 1.23 times 10 to the 8th. You can also think of it as jumps. So if we want to put this decimal, so watch down here. We want to put this decimal right here, and we know it ends up over there. We can count the number of jumps, and that is the exponent. So 1, 2, 3, 4, 5, 6, 7, 8 jumps to get the decimal there. Well, that's 1.23 times 10 to the 8th. How about for very small numbers, scientific notation for very small numbers? Again, we want it in this format. Well, here's the number. This is a very small number, and this is the 10 to the 0 is the units place value. That's 10 to the negative 1, negative 2, negative 3, negative 4, negative 5. So if we go like this, 5.68, ooh, see here we round up, 5.68 times 10 to the negative 5th. But again, I like this jump. So let's count here. 1, 2, 3, 4, 5 jumps to get that right there. And so that would be 5.68 because that's bigger than a 5. So 5.68 times 10 to the negative 5th. We jumped 5 times. Now, how do you know it's negative? Because a small number, negative exponent. So if it has a positive exponent, that's a very large number, and a negative exponent is a fraction, a decimal or a fraction. Okay, rewriting in proper scientific notation. Sometimes you get an answer, but it's not in proper. This is not proper scientific notation. Remember, the decimal is supposed to be right there. So how do we fix it? Well, this is incorrect because the decimal's in the wrong place. So where does the decimal go? It goes right there. So I made this number here, 563, I made it smaller by 2 place values. 2 place values. So I have to make this number bigger by 2 place values. So I added 2 to 4 to get 6. So I made this smaller by 2 place values. I made this bigger by 2 place values. That's how I like to think of it. So this one here, this is incorrect. So we want to have the decimal there and just these 2 decimal places. So we're going to have 4.32. That's correct. But we made this number bigger, so we have to make this number smaller. And we made this bigger by 1 place value only, and so we make this smaller by 1 place value. So I hope that shows you how to rewrite your answer or rewrite a number in proper scientific notation. Okay, and so here's another example, 79.5 times 10 to the negative 4. This is a little bit tricky because people get confused with negative numbers, but here, 79.5, did I make that number bigger or smaller? I made this one smaller by 1 place value, so I have to make this one bigger by 1 place value, and negative 3 is bigger than negative 4 by 1 place value. Here's a hard one. Oh my goodness, look at this. This is not right. So we're going to go like this. 1, 2, 3, 4. Uh-oh, that's not right. So 1, 2, 3, 4. We changed that by 4 place values. And so this is correct. But if we made this bigger by 4 place values, which we did, 1, 2, 3, 4, then this should actually be smaller by 4 place values. That would be 10 to the negative 9th. So I didn't catch that mistake I made there, but that should be just, that should be 10 to the negative 9th because we changed it 1, 2, 3, 4, and then this one should be, I made this 4 place values bigger. I have to make this 4 place values smaller, and negative 9 would be the proper there. Operations with scientific notation. This is important because scientists, of course, add and subtract, multiply and divide numbers all the time. And so we use scientific notation, and adding and subtracting is actually a little bit harder than multiplying and dividing. It is recommended, and this is how I do it. So I'm going to say it's recommended, but that's how I do it. Recommended to change the power of 10 of the smaller number to match the larger number. So whatever the smaller power is, we're going to match it to the larger one. This is like lining up the place value. So let me show you an example here. So what is the sum of this and this? Well, you can't just add 5 plus 4 because this 10 to the 8th is not the same place value as 10 to the 6th. So what I recommend you do is make this smaller place value the same as the bigger. So I made this bigger by 2 place values, so I have to make this 4 smaller by 2 place values, and now the numbers or the decimals are lined up. So we can have 5 plus 0.04, well that's easy, and 10 to the 8th, so that's 10 to the 8th, you do nothing to that. So 5.04 times 10 to the 8th. Let's look at another one. Here's how much more, this is a subtraction problem, is 4.3 times 10 to the 5th than 6 times 10 to the 4th. How much more is a subtraction problem? So, well, 4.3 times 10 to the 5th, that's the bigger one. And we're going to subtract this smaller one, but we don't have the decimal or the place values lined up. So we're going to make this 4 into a 5. I made that number bigger by 1 place value, so I have to make this smaller by 1 place value. And then we have 4.3 minus 0.6. Well, that's 3.7 times 10 to the 5th. And of course, we should always check, is that written in proper scientific notation? And it is. So, and here is just a reminder of that. If your answer is not written in proper scientific notation, you should rewrite it. But we got this answer, then we should make this one bigger by 1 place value, and this one smaller by 1 place value, and it'd be like that. And you might practice some of these when you, if you want to come back and practice some of these, changing them into proper scientific notation. Okay, multiplying and dividing. And so in area, or anything where you're multiplying really, really big numbers, of course, and if you want an exact answer, you might not use scientific notation, but if you want an estimate, this is perfectly okay. So what is the area of a rectangle with sides 6 times 10 to the 7th meters and 3 times 10 to the 3rd meters? So you might think of a county or something as this size, I don't know. So 6 times 10 to the 7th times 3 times 10 to the 3rd. So, well, that's pretty easy. And I'm going to rewrite this using the commutative property of multiplication. I can put the 6 times the 3 together, and that's 18, and the 10 to the 7 times 10 to the 3rd, well, I remember from last week when you multiply exponents with the same base, you just add their powers, so that's 18 times 10 to the 10th. Well, that's not in proper scientific notation, so we'll make this number smaller by 1 place value and this one bigger by 1 place value, and there's your answer in scientific notation, 1.8 times 10 to the 11th meters squared. Here is a division problem, a very important type of division problem. How many times more? So how much more? Subtraction problems. How many times more? This is the division problem. 2 times 10 to the 8th people. So if we think of that, that's like 200 million. How many times more is 200 million than 4 times 10 to the 6th, that's 4 million, I believe. So how many times bigger? And this is a division problem. So, of course, we could fall back and do it and write out all the zeros, but we don't want to do that. We're going to learn how to use scientific notation. So we'll write it as a fraction here, and we'll put this 4 times 10 to the 6th on the bottom. And here, 2 divided by 4, well, that's 0.5. And then this part, 10 to the 8th divided by 10 to the 6th, well, that's a subtraction problem. We learned that last week, and those have the same base, so that's 10 to the 2. So here we have the answer, 0.5 times 10 to the 2. Well, that's not proper scientific notation, so we make that bigger and make this one smaller. Well, how many times bigger is that? So 5 times 10 to the 1st, well, that's 10. 5 times 10. And oftentimes when we write these types of problems, how many times more, we write the answer in standard form. So 5 times 10 to the 1st, or 50 times more. So thank you so much. That's the lesson on powers of 10 and orders of magnitude and scientific notation. I hope you enjoy your practice set. Thank you, and have a good day.